Part 2 deals with the essence of system thinking. The content of part 2 is the essence of system theory. We are selecting a few criteria that we feel are representing what system theory is really about, and they are going to be emergence, co-production, synergy, and mutual interaction. We are also going to look at what systems are by definition. And then essence of systems methodology. We are looking at methodologies like iteration, managing paradox, limits, self-referral, etc. Essence of system theory. First of all, what is a system? There is many definitions around as there are system thinkers, and we just give one by Eckhoff and Garchedaki. A system is a whole that cannot be divided into independent parts because the behavior of the parts and their effect on the whole depends on the behavior of all the parts interacting with each other. So if you unpack that a little bit and also add what other system thinkers say, then the elements of systems definitions usually start with it's a discernible whole. So a system, intuitively we know that something is a system because it's a whole in its own right. It consists of parts that interact with each other and parts that are organized for a purpose, whereby the interaction and the purpose of the parts is directed at the function of the whole. So if our whole is a car, then the parts interact in a purposeful way to give rise to the function of the car, which is driving. And systems have regulated relationships. In other words, the behavior or the interaction of the parts is also regulated. Besides having a specific purpose, there are specific regulatory criteria within which behavior occurs. In the body, we call that homeostasis. And the interaction of parts and their purposeful behavior gives rise to emergence at the level of the whole. Emergence means that the whole has properties or qualities that the parts do not have. So, for example, the car can drive. None of its parts can drive. Biometric systems theory has its own definitions. We are also distinguishing between different types of systems, and we have different definitions for those. And we are going to talk about that in the section on biometrics key concepts. The essence of system thinking is probably best described by the concept of emergence. It is described by that famous saying, the whole is greater than the sum of its parts. What that means is that the whole has properties or qualities or characteristics that are not inherent in the parts. So they emerge at the level of the whole. The car drives, so driving emerges as a quality at the level of the whole. None of the parts can drive. The driving occurs out of the interaction of the parts. We can illustrate emergence with the case study of water. Water consists of hydrogen and oxygen atoms that interact with each other and give rise to water, H2O. So what are the properties of water? Well, water is liquid, it changes shape. In other words, if we pour it into a glass, then it takes on the shape of the glass. There are other characteristics, it may be clear, it's wet, etc., etc. Where do these properties come from? The hydrogen or the oxygen? Well, they arise in interaction of the parts of the system. Of course, H2O is not only water, it can also be ice or steam. So if we are looking at the different properties of those states of water, then ice is not liquid like water, it is solid. it keeps its shape. So if we're putting ice cubes into a glass, the ice cubes do not take on the shape of the glass, but stay the shape they were in. Steam, again, has its own properties. It is gaseous, so it's not liquid or solid. It does change shape, but maybe not to the same extent as water does. Why are ice, water, and steam, if both of them are consisting of hydrogen and oxygen, why are they giving rise to different properties? The reason is temperature and pressure. So in interaction with the outer and inner environment gives rise to different states at the level of the system we are looking at, like water. It may be useful to mention here the difference between holism and holism. The difference lies in the concept of emergence. Normally, when we talk about holism, system thinking is a holistic way of looking at the world, then we emphasize that we must look at the whole and all its parts. While if we are looking at holistically at the world, then we are looking at wholes in terms of having unique properties as distinct from other systems. So holism emphasizes emergence, and it was coined as a term by Jan Smuts. In summary, holism, spelled with a W, emphasizes parts forming a whole, while holism, spelled with an H, emphasizes emergence, namely that there are emergent properties arising at the level of the whole which are not inherent in its parts. Another concept is co-production or co-causation. Everything in the universe is co-produced or co-caused. Water, ice, and steam are co-produced or co-caused by the interaction of hydrogen, oxygen, temperature, and pressure in the outer and inner environment. So co-production in many ways is the reverse side of emergence. So the co-production gives rise to emergence. We also distinguish in system thinking, when we talk causation, between necessary causes and co-factors. There are some situations which are brought about by a necessary cause. Oxygen and hydrogen are necessary causes of water. If we wouldn't have those two atoms, they wouldn't give rise to water. But they are not sufficient. They also need temperature or pressure. Likewise, if you're looking at a disease such as HIV/AIDS, for example, HIV/AIDS has a necessary cause, the virus, which needs to enter the body, but the virus alone is not sufficient. It needs cofactors for entering the body, and those cofactors are derived from the environment. So typically, when we look at co-causation and co-production in system thinking, we are not taking a singular look at causation. There are systems where it may be difficult to distinguish what are the necessary causes, and we focus more on co-producing factors. In the social domain, for example, if you're looking at how does an organization develop, it is very difficult to single out a necessary cause. It is co-produced by many cofactors, and they can range from the strategies of the organizations, its vision, missions, culture, the way it interacts with the environment, the way it manages its processes, designs its structures, develops its resources, etc., etc. So there are numerous cofactors that interplay and give rise to how an organization develops. Also, problems are co-produced. Systemic problems have lots of co-producing factors. If we are looking at an education problem the education problem in developing countries, we use here the word mass education, mass. Then we have numerous cofactors that range from poverty in the environment, not enough resources, unmotivated parents, children, teachers, crime, vandalism, insufficient resources, inappropriate curricula, wrong policies, insufficient teachers, etc., etc. Numerous problems that interact with each other and give rise to very messy problems that are difficult to dissect. System thinking tells us about another important aspect of co-production, namely that small cofactors can have a very large effect. The famous saying of the last straw that breaks the back of the camel illustrates that. Chaos theory talks about the same phenomenon, calling it the butterfly effect. The butterfly effect is ascribed to Edward Lorenz, an atmospheric scientist who developed computer models for weather forecasting. He found out that if one of the variables is changed in a minute way, then the effect of the outcome of the forecast can be completely different. The reference to the butterfly comes from one of his scientific papers, which was entitled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" In a nutshell, what all this means is that because of co-production and emergence, some systems are appearing to be disorderly and chaotic. They are messy, as Eckhoff called them. They are also unpredictable because small changes can have a large effect in the future. Some systems thinkers talk about synergy or dyssynergy as being the essence of system thinking, and they equate that to emergence, while others say synergy is really defined as co-production and emergence together. Like synergy arises from parts working together to produce desirable emergence at the level of the whole. If co-production produces undesirable emergence, we typically refer to it as dyssynergy. The synergy or dyssynergy can be illustrated by the famous saying, "Perfect parts do not make perfect wholes," famous saying by Eckhoff, and he gives the delightful example of, "Let us design the best car in the world." Wouldn't it make sense to create the best car in the world, to look at what are the best parts in different car models and bring them together and patch them together? So we take the chassis of the one and the motor of the other and the gearbox of the other and so on, and we put them together in a car. We would get the best car in the world. Well, the answer is no, we will not. And the reason for that is, as one of my MBA students once said, is the parts don't talk to each other. They're not designed to interact optimally to give rise to a desirable outcome. We optimize the parts and as a result sub-optimize the whole. If we were to optimize the whole, like the car, the first question we would have to ask is, what do we mean by best car? Do we mean best racing car, or best car for a town, or best car for long distance driving? There would be different criteria that define what best is, and then we would have to design the car to meet those criteria and the parts to meet those criteria that we determine at the level of the car. If we give an example of an organization, we have optimizing or dyssynergy problems very often between the two functions, marketing stroke sales on the one side and production function on the other side. Marketing and sales tends to emphasize the increasing of sales, the increasing of market niches, of developing new markets, maybe even developing new products in order to get more markets, while the emphasis in production lies on efficiencies, low cost, high quality, meeting target, safety, and various other criteria. To achieve increased marketing, we need to customize. To achieve increased efficiency and all the other criteria that we want to have in marketing, we have to standardize. So the more we customize, the more we can sell, the more we standardize, the more efficient our production will be. If we customize too much, the danger is production cannot follow. That is a typical case in many IT companies where the marketing team goes out, does a feasibility study, sells a project to a company, clinches the deal, then hands over to production and say, do it. Or in some engineering projects, that also happens frequently. Production says we cannot meet those specs that you negotiated at those prices, at those time frames, cannot be done. So we call it typically overselling and under-delivering. The opposite can also happen. We can have very efficient production, very low cost, thanks to standardization, but we have no markets to sell to because we have neglected the marketing function. Where do we optimize? Well, we have to optimize at the level of organization. We have to find the right mix between customization and standardization so that we are not optimizing either marketing or production and sub-optimizing the whole. So optimization must be at the level of the whole organization. Another important concept of system thinking is that of impact. As one system impacts on another system, it elicits a response in that system, causing a change in that system, and that change may cause a response again in another system. So if I am teaching you system thinking, maybe you're learning something new, think about some areas in your life differently, and respond in future differently in those areas of life, and causing changes there also. So the rippling of change from one system to another is explored in systems dynamics models. The famous proponents include Forrester, Peter Senge, and Gomez, amongst others. If you're looking for an example of systems dynamics model in the context of organization development, we could say business development requires organization development. In other words, if I, for example, want to expand my business maybe into another country, I have to do more organization development. This could involve creating a new IT system and maybe also skills development. These in turn, my IT development would have an impact on skills development. It could allow more skills development to happen, maybe through e-learning. It could also mean it will be required to change the skills of the staff in the organization in accordance with the new developments in IT. IT development will also allow more organization development and more business development. Likewise, if we improve the skills of our staff, this will impact on business development. And business development in turn will allow us to learn more about business and will also contribute to skills development. Here is another comic strip type of systems dynamics model that we experience every day. Frustrated husband shouting at the wife who burns the food, who feeds burnt food to the cat, frustrated cat scratches the baby who screams, and so on. If we were to turn around the errors in a different direction, we would get another systems dynamics model or another scenario of the home life. Such systems dynamics models can be very useful tools for exploring our lives, work life, family life, our conflicts, our problems in life, and so on. Another case study, if we go back to our education system example, and we look at the different co-producing factors, and we are selecting a few and use them as variables in a systems dynamics model, what we can do is we look at the impact of those variables on each other. So they are not only cofactors giving rise to an education problem, but they also impact on each other. Now, those are some of the impacts that were once plotted by a group of teachers who had a look at that model. A systems dynamics model illustrates how one area impacts on another area. So if we are changing something in the one area, it will impact on another area, denoted by the impact error. And because something changed in that system, there will be an impact on another system, which, having changed, will impact on the next system, and so on. So if you have a model like that, we can walk our way through the different impacts and changes that will occur. And typically, if I'm making a change in any one of those variables, it will ripple through and even come back to the original variable itself. That is why systems dynamics practitioners call those impacts feedback. Because depending where I start, something comes back to something else. Systems dynamics model also shows multiple causation or co-production. So whenever several errors go into a variable, the other variables from where those errors originate are co-factors to that particular variable. There are also system thinkers who distinguish between active and passive variables. Fester, for example. He would say where many errors go into a variable and few go out, this is a passive variable. It is impacted on by a lot of other variables, but has very little impact itself on other variables. Other variables have a lot of errors going out. That means they're very active. They impact on a lot of other areas. So when we design change interventions, we will not waste our time to try and change passive variables. We will put our money on the most active variables and make change interventions there, because through those variables, change ripples into the other parts of the system as well. We can also see that some variables are connected through direct mutual impacts. An example is how teacher motivation impacts on pupil motivation and pupil motivation impacts on teacher motivation. And it is very difficult to say in these situations where is the original cause coming from. So if one has a very dynamic and very motivated class, was it the teacher who stimulated the pupils, or the pupils who stimulated the teacher, or both? We call those mutual impact circular causation or mutual co-production. The famous example of circular causation is, of course, the chicken-egg situation. What was first, the chicken or the egg? It cannot be said. They mutually depend on each other. And circular causation can involve vicious circles. I hit you, you hit me back, I hit you harder, you hit me harder, speak, conflict zones in the world. There can also be virtuous circles. I'm nice to you, you are nice to me back, I'm even nicer, and so on. How does one change a vicious circle? By trying to convert it into a virtuous circle. How can that be done? By not retaliating. So if somebody hits me, I do not hit back, I turn the second cheek. This is a very dangerous strategy, of course, because one might not survive that particular strategy. But if it succeeds, it is very powerful in creating a virtuous circle, especially if the more powerful party is turning the second cheek. Do we have examples where that happened in society? Yes. South Africa is an example. After the transition from apartheid in 1994, it desisted from retaliating, but instead emphasized forgiveness, reconciliation, and the Truth and Reconciliation Commission, and of course Mandela had a great role to play in turning a potentially disastrous situation with potential civil war into a virtuous circle that South Africa represents now. All right, let us summarize what the essence of systems thinking is about. Systems thinking is about emergence, that properties arise at the level of the whole that are not there in the parts. An organization can have characteristics that are greater, more different than the sum of the parts, the sum of the staff, for example. Co-production is another essential concept of system thinking, and it implies that any outcome is typically co-produced by different cofactors or different causes. So there is not a singular causation. Synergy represents the co-production of desirable outcomes, while if co-production is conflictual, it is giving rise to dis-synergies. And this is a very important concept in system thinking. And then there is the concept of impact, that one system impacts on another system and as a result causes change in that system, which in turn impacts on other systems and causes change there, and that change is rippling through all life at all times, and we can use systems dynamics models to plot how that change occurs.